am so happy to have Cathy Fitzgerald with us today. So Cathy is a geologist with almost 20 years of exploration and resource development experience. She's currently the Vice President of Exploration for Apollo Silver Corp and is responsible for the company's exploration strategy, deposit geology development, and resource advancement. And it is going to be awesome hearing from her today about how they illuminated the Waterloo silver deposit using their full element suite to support logging and 3D modeling. So this is going to be an awesome session. Please keep using the chat. We'll open up the floor at the end. And thank you so much, Cathy, for joining. It's amazing having you here.
Oh, thanks. I'm not going to lie. I'm extremely nervous, everybody.
Don't be.
So in our project, I'll give you all the details, but our project's in the Mojave Desert in California, and there's a group of retired USGS geologists or ex-BLM managers who run an event called the Desert Symposium every year, and it's all volunteer, but basically they get together anybody who wants to attend, whether academia, industry, anybody who likes prospecting, and they do a tour of the Mojave and 2 days of talks for whether it's mines or geology or fossil hunting or whatever. So this year's topic was Mines of the Mojave. This coming year's is Trails of the Mojave. So whether they're donkey trails or, people trails. So we participated as part of that symposium. And so myself, Chris Gallagher, who is the principal of his own consulting company called Road Geoscience, and Dr. Warren Pratt, we threw together a paper on our work at our Waterloo silver deposit for that event, and then also just gave a presentation and hosted people at the project. So, myself, I've always been a big fan of sharing science data because, none of us will be successful, I don't think, if we don't share our knowledge. This particular project, like I said, I'll get into the details, but it's been around a long time. The district is hundreds of years old, and we wouldn't have been as successful as we feel we were if we didn't have prior scientific knowledge shared with us. So I'm just going to tell you a story. I'm not going to tell you how to do geochemistry or how the details of how we did things per se. It's more about how we achieved our company goals with this deposit, supplementing what one could call traditional information such as visual logging and mapping with looking at our full element suite. I've had over my 20 years most of it with, I spent 5 years with Ivanhoe Electric, and now I've been in the group I'm in now for 2.5 years. So over the last 7.5 years, reviewing a lot of projects. And I can't tell you how many I've seen where people pay to analyze their full data sets and look at only gold or look at only silver. And they're just leaving value on the table, not only in possible other elements that might be economic, but in really understanding their deposit. So, I'm not going to go out and do a geophysical survey. I'm going to hire a geophysicist who knows what he or she are doing to do a geophysical survey and interpret the data. It really should be no different with your geochemical data. You're paying for it. Get the full value out of it. Hire a geochemist if you don't have someone internally who can do that. That's my advice. So typical cautionary note, this is presentation on our corporate work, so I have to throw all this stuff up. You can read it on our website if you want to. So in my summary, I talk about using chemistry to supplement our visual logging to build a robust 3D geologic model for resource estimation purposes. So I'll take you through the history of the deposit and the geology before I take you through what we did. We didn't really do that in our Desert Symposium talk because all the people we were talking to are well familiar with the deposit. So apologies if I'm repetitive or miss something. So this is the first time I'm giving this talk this way. So it's an old district, lots of work on it. So we had the goal of using as much historic data, whether like drilling data, geologic mapping, to declare an initial mineral resource estimate. And we did that using only historic data, which isn't totally common in the industry, but to tell you that the quality of the data we had all the pulps, all the RC chips, all the core. We could, everything that was historically drilled, we had not only the logs, the data, but the material. So it was really reliable. We declared an initial mineral resource estimate on historic data alone. And then that allowed us to use less drill meters to increase the confidence of that resource. So as a further refinement of our program, and again, trying to achieve the biggest bang for our buck, we wanted to use our full element suite too. And so the results of a rigorous analysis of that were identifying key elements that could fingerprint geologic contacts, which we could not distinguish visually because a lot of the drilling here was RC. We could highlight key stratigraphic horizons that helped us target more or higher grade silver, and highlight the presence of gold that no one really had paid attention to before beyond what was exposed at surface. And we identified important vectors towards mineralization. So learnings from this work allowed us to not only reach our resource goals ultimately, but to complete real-time targeting while drilling using a portable X-ray fluorescence tool, particularly for gold. And PXRF is not ideal for analyzing for gold itself. So using vector elements was that it could measure was very valuable for us. And so this slide just shows the final resource. So measured is in red, orange is indicated. So we have 160 million ounces of silver across 2 deposits here. I'll give you an overview of that shortly, but 110 of that is at the Waterloo deposit and 70,000 ounces of gold. So we declared this in March 2023, and it's based on, well, I have 50,000 here, but that's for both deposits. So based on 30,000 meters of, 28,000 meters of drilling just at Waterloo. You can see on the image on the left, we have a gold horizon underlying a silver horizon. So I'll walk you through, how we identified that and defined it. And why did we have such a focus on chemistry? So I won't leave out that I think Cam mentioned both my degrees are in geochemistry. So I studied alteration of seafloor basalt by hydrothermal fluids at active and inactive hydrothermal vent sites for my master's degree and for my bachelor's degree. And Chris, our co-author, is a geochemistry wizard. So we're just naturally inclined to look at all our data and see what we can figure out from it. I mentioned most of the drilling here was RC. So, and that's not only ours, but historically. You'll see the rocks in a bit. All the rocks are highly silicified and brecciated, and drilling is quite difficult here. We do have some core, but really a lot of it's RC. And from my understanding, a lot of RC is done in Australia. So maybe if the work we did here can help some people, that'd be great. So for those of you who don't know silver, like my talk kind of wants to target everybody, but silver is very important industrially because it's the most conductive and reflective metal, and it's very malleable. So it's commonly used for microelectronics, switches, circuit boards, computers, and even in automobiles. And of course, it's been used for centuries in jewelry and coinage as well. Mostly it's shiny, malleable features. So a small part of overall silver demand is in solar panels, but this is growing. In 2023, the Silver Institute estimates up to 14% of silver consumed will be used in panels, up from 5% in 2014. And researchers estimate that will increase to 20% by 2027. So despite the fact that silver demand is growing faster than supply, it's not on the Canadian or US critical minerals list, and that's primarily because it can be acquired from friendly nations such as Mexico. One of the challenges is the processing of silver to be used in solar panels is really not domestic. I think there's one plant in the States. A lot of it is in China. So there's other parts of the value chain that aren't represented domestically that really should be, to achieve, countries' greening goals. The other thing is about 80% of supply of silver comes as a byproduct of other mines. So lead, zinc, copper, and gold. So this is an interesting deposit worldwide simply because it's primarily silver. So it's the Calico projects. It's 2 deposits across technically 2 land packages. So Apollo acquired these in 2021. We purchased Waterloo, the private land and the deposit from Pan American Silver. And we have an option to earn in 100% of the adjacent Langtree from a private vendor in California. So this is the first time the projects have been combined under one ownership and studied really together. ASARCO had owned Waterloo years ago and had done work on Langtree, but from all the work we've seen, no one's ever really studied them together. I am going to be focusing on Waterloo today, mostly because most of the silver's there, most of the work has been there, and the mineralization is at surface at Waterloo. At Langtree, it's about near surface to 60 feet under cover. So really, I'll just focus on Waterloo. The project is right in the center of the Mojave Desert in San Bernardino County, which actually is a very active county for mining. They have more than 80 active mines of aggregates, gold, and the Mountain Pass rare earth element mine, for example, the only U.S. operating rare earth element mine is present in this county. These deposits are interpreted to be erosional remnants of a formerly continuous Miocene stratiform deposit. And it's hosted in siliceous sandstones and siltstones. And it's interpreted to be syngenetic, low temperature, hot spring style with replacement origin. A little history, just because I think it's cool. The deposits lie on the western edge of what's called the Calico Silver Mining District, which has a long history of exploration and mining, and it's very well documented. Silver was discovered here in 1881, with mining beginning soon after, focusing on the these high-grade, supergene-enriched, oxidized silver barite quartz veins. They are high-angle, northwest-oriented faults, all located in these what we call, what's been named the Pick Handle Formation, which are volcaniclastics, andesites. Grades of these high-angle veins can be in excess of 1,000 grams per ton, which I guess is 32 ounces per ton. Forgive me if I don't always do that conversion. So surface and underground mining was active here up until 1896, when the silver price declined and deepening workings depleted silver ore as the water table was approached. I did mention it was oxidized. So a reported 15 to 20 million ounces of silver was produced from about 50 mines. So of these mines, only 5 were hosted in Miocene barstow sediments, which are derived from the erosion of the Pick Handle volcanics, some people think. And it's these barstow sediments that host our deposit, Waterloo and Langtree. There were only 5 historic mines in the sediments. After 1896, there was intermittent further periods of mining of more silver, along with barite and limited gold up until 1940. And so one of the largest mines active during this time was called the Waterloo Mine, which is located on our property. And it is hosted in those sedimentary rocks at the contact with the Pick Handle volcanics. This is a relatively high angle contact. Regionally, it's been described as unconformable. Locally, Dr. Warren Pratt, who's done 3 tours of mapping here and is our co-author, he consulted for us and did some mapping as well. He says it's conformable in some areas, appears conformable in some areas, and it's very befaulted and brecciated in others. So part of the mysteries here are, what is the nature of this contact? We aim to be working with a University of California, Santa Barbara student to help us figure that out. And she's going to also do some further age dating on the mineralization here and some mapping. And that's important for us to better understand, more high-grade silver, or how does it relate to gold? I'll get to that later. So you'll see the Bircham gold mine on the right. So it was about 1940. Gold was extracted from 2 underground drifts that followed high-angle, high-grade, I say high-grade, up to 10 grams per ton we've sampled on surface from high-angle structures. And they're similarly oriented to that Barstow pick handle contact. I should say a reported 6 million ounces of silver was extracted from Waterloo along this contact, which is interpreted to be replacement style silver, and grades were up to 700 grams per ton, and workings are over 7 levels. So this Bircham area is interesting in that, I don't actually know who did that mining in the 1940s. I do know ASARCO did some underground sampling and mapping, and they also did limit like 10 short rotary holes to determine that the sedimentary package here holds disseminated gold as well. So they did some amazing work, and so did Pan American. But so, here's an example of an old map. We really had some awesome stuff to work with to really give us a leg up on interpreting this deposit using new tools, so 3D modeling, iogas, et cetera, things they didn't have available back then. So it wasn't until 1963 that the stratiform silver mineralization was discovered in the sediments here by ASARCO. The adjacent Lang tree that I've mentioned was discovered a year later by Superior Oil. So the average grade in our resource at Waterloo is 100 grams per ton. Lang tree is about 89. Between their discovery and 1989, there was significant work completed at both deposits, more so at Waterloo by ASARCO, who actually received a permit to mine in 1981 that was valid for 24 years. So the photo there on the upper left is a picture of a scale model of the future Waterloo mine. We have acquired some old pictures of the rotary drilling, and then the map on the right was a result of 6 months of mapping and core log, apparently there's some core that was logged, but RC drilling, logging, and cross-section making and surface sampling by Ian Darby Fletcher, and he wrote a PhD in 1986. So we have all that historic information. So the geophysical surveys, for example, there were magnetics, EM, gravity, and IP, not only over the hills here, but you can see that flat area where tailings pile. They've done a lot of work all through the flats in order to determine where to put their facilities. And then when we came in, basically over both deposits, we had more than 40,000 meters of drilling. I think about 18,000 is at Waterloo. Between 2012 and 2021, no work was completed here, until we came along in 2021. So geology, the Calico mining district is located in the western edge of the Calico Mountains, within the center of the Mojave Desert. So this region experienced widespread volcanism during the late Oligocene, early Miocene, about 24 to 17 million years, during northwest to southeast crustal extension. Lesser volcanism was occurring about 17 million years. So the mountains are primarily comprised of what I've talked about, the pick handle volcanics. They formed around 19 million years ago by rapid deposition into a basin formed by a proto-Calico fault, and the Calico fault is highlighted in red. A last gasp authors think of extensional volcanism is these dacite domes, and they're dated about 17 million years. And that is the age of the one age date we have for mineralization at Waterloo by Fletcher. So quite a few authors interpret these whatever event was associated with emplacement of these late domes as the heat engine for the low temperature, low sulfidation silver mineralization here. I should also mention that the mineralization in the veins in the pick handle that were historically mined are paragenetically similar to what we see in the stratiform deposits. So all the mineralization, whether it's in volcanics or sediments, is interpreted to have been formed by the same event. it was between 19 and 13 million years that syn and post-extension sedimentation in a shallow lake formed the Barstow Formation sediments. And there was a period of transpression between 17.1 and 16.8, where the Calico fault and other normal faults all through the mountains here reactivated. It was during this time that the sedimentary package was folded. So I'll show you cool pictures of that too. So also note that the Waterloo deposit occurs at a flexure or restraining bend in the Calico fault, and it's here where there's a local zone of thrusting, which caused significant post-mineral brecciation of the deposit. And then this fault is also important because it forms the western boundary to mineralization as we know it today. Sarko speculated that more of the silver mineralized package could be present at depth underneath the Calico fault. We haven't taken the opportunity to explore for that, as our initial goals were a resource estimate. So here's a map of Warren's mapping, Chris's mapping, and put onto topo. And essentially this is our initial 3D model. So it's just showing you the general distribution of silver and gold. Silver's in, well, let's make it work. Oh, there we go. It's in blue and the gold is in red. And so the network of faults, that is the Calico fault system here. Historically, Sarko and other workers would call, some would call this strand here in the middle of the Calico fault. Then they later started calling this the Calico fault and this the Enigma fault. So really it's a system. We can't think of it as one fault. So as I mentioned, the thrust, the westernmost portion is this thrust fault that is thrusting mineralized lowermost Barstow rocks that are along in contact with uppermost pick handle with a younger non-silver or gold mineralized package of Barstow. We have ideas on the age of this package of unmineralized rocks simply from fossils. So there's camel fossils, for example, in this portion, because there was actually a land mammal age, Barstowian land mammal age around 10 million years. So there could be as much as 17 million years of strata, or 7 million years of strata missing here because of the thrusting. So the mineralized portion of the Barstow, I mentioned it's oxidized mineralization, stratabound disseminated silver. It's occurring within a sequence of variably silicified and variably bleached fluvial and lacustrine sediments. The package is tilted down towards the northwest here. So the deepest portions of the strata are exposed here where the gold is exposed at surface. So here we interpret that erosion has removed overlying silver. The underlying pick handle here in contact with the Barstow are commonly these tough, rich volcaniclastic rocks. In some areas in Langtree, for example, there's thrusting where these are also thrust over Barstow rocks. So it's quite structurally complex in some areas. I'll talk a lot about the Barstow pick handle contact because it is the gold host. And I'll probably talk a lot about Calico faults. Again, apologize if I'm repetitive. So the silver deposit I mentioned is hot spring style and developed in a non-marine sedimentary basin, and it was strongly controlled by active faults. There's several through-going high-angle faults within these sediments, similar orientation to what was mined historically in the pick handle. Timing, like relationships and timing, there's still nitpicky things we haven't exactly worked out yet, but it's evident that the highest grades of gold in the Barstow occur in these high angle structures, and the highest grades of silver within the stratabound package occur where high angle structures intersect presumably receptive beds of the Barstow. So like I said, there's still things to work out here, but we could use these kind of things to target higher grades in our drill program. So I mentioned 3 styles of mineralization, but just to recap, both silver and gold in the district, and frankly, on our project, are 3 styles. Stratiform and disseminated within quartz, barite, and adularia altered sediments. The adularia is very fine grain. You can only see it in petrographic analysis. And actually, the silver and gold are both fine grained as well. You cannot pick up a rock here and say there's silver or gold in it. Mineralization is also vein style. So this is a good picture on the lower right. There's later veins that are emplaced within the earlier silicified barite rich stratiform rocks. And it's also replacement style. So that historic Waterloo mine was in we think, a broken and brecciated portion of the Barstow pick handle contact. And so the metal fills open spaces. Unfortunately, we couldn't map that Waterloo mine or drill there. Like those historic workings, dangerous. There's a lot of collapsed areas around there. So we kind of had to stay away from that area. So yeah, this is just an example of silver mineralized sediments. So this is nice siliceous sandstones. There's quite a lot of barite in this deposit, which is really a story for another day. On the right is a laminated siliceous interpreted formal algal mats with convex upward growth. So Warren, when he was doing his mapping, there was lots of evidence for syngenetic silver mineralization here. We actually do also have stromatolites, historic stromatolites on both deposits. It's very interesting, geologically in terms of how this deposit came about, but literally just looking at the rocks is cool. Like there's stuff here I've never seen before, like on the right, sandstone dikes with open spaces filled with barite. So Warren has done a lot of work on low temperature epithermal deposits. Silver, this is comparable to Navidad, which is another deposit of Pan Americans, for example. On the left is the upper pick handle lapilli tuff breccia. So this is what the pick handle looks like at the contact with the Barstow, and it hosts gold. We do not know yet how deep it hosts gold. It seems it's open at depth right now. So I think we've drilled down to 80 meters. And the grades for gold are low in the disseminated portion, anywhere from 0.25 to maybe 2 grams per ton. But there's definitely more work to be done there. The gold was our focus initially was declare a silver resource. The gold was a sweetener on the side when we figured out there was some spatial continuity to it. So what's important, I mentioned we did RC drilling. This rock on the left, when it's steam heated, altered white, it was essentially indistinguishable from the lowermost Barstow Formation rocks, which were sometimes a white, altered, pebbly conglomerate. And distinguishing this contact became important because it was the termination of silver mineralization and the beginning of gold. So we needed to understand where that was, and identifying that visually wasn't always easy. So that's where chemistry played a part. So on to fun stuff. So this is a cool outcrop. So a mile from the edge of our Waterloo project is a San Bernardino County run ghost town park. And so it's called the Calico Ghost Town Park, and was restored by Walter Knott, of some of you in the US might know Knott's Berry Farm fame. So it's a big tourist attraction for the county, and it's the town that was built up during the mining in the late 1800s, and it's been restored. But as part of that, there's this incredible exposure of the folded Barstow sediments. So off to the right here, which I can't even show, but the exposure is about 3 times longer, and you can walk from the Barstow pick handle contact right up to the Calico fault here and see how the strata progressively gets more folded until it's almost vertical along the contact. So geologically complex in terms of folding, faulting, and so we needed to model that to better understand the controls on our ore distribution. And we wanted to use the model to test hypotheses related to targeting structural intersections, adding more high value or high grade silver or more silver in general, and understand the gold. And we also wanted to use our model as a dynamic tool to refine our drilling. So can we to be smart about our drilling, so not be chintzy and cutting out on drill meters per se, but use our drill meters smarter. So and I'll go into details, but if there's, say, indicator elements that will tell us this is not going to be a gold mineralized zone, we can save our drill meters there and go somewhere else. Risky, yes, but ultimately when we got all our assays, we were really happy with the results, and this worked out really well for us. So Chris Gallagher did our modeling as a consultant for Apollo. I don't know if it matters, but it's interesting. Chris and I have known each other for 25 years. He was actually my TA in university. So he gets a big kick out of the fact that he gets to work for me now. But so he's very talented in modeling and chemistry, and he's worked on deposits all over the place. And I'm just thrilled with the work he did here, using Warren's mapping, our chemistry to, help us achieve our goals. So I'm going to try and play a movie. Let's see. Does it work? Yeah. So the first thing Chris did was define in 3D fault-bounded domains, which constrain zones of variable geology, alteration, silver distribution. Changes across these domains are sometimes minor, sometimes major. So in terms of strata tilting or silver distribution, we can see big differences in some cases. So the Calico fault's shown here as the surface. And so we used actual fault measurements from mostly Warren's mapping, three tours, 2 for Pan American, 1 for us, to build these structural domains along with pierce points. A lot of the Asarco drilling was very short. They really were only targeting this uppermost highest grade silver. So we didn't have a lot to work with here. You can see the yellow dots are pierce points for the Calico fault. And those are a lot of them from Pan American drilling. So this is a first model we made with only historic drilling. We hadn't started our modeling yet. So Chris repeated this process for all major faults, so producing a number of fault-bounded domains whose internal geology was then modeled independently. Is this the same video? It is. Okay, so here we go. Apologies for technical difficulties. Oh, it's working. So each domain is highlighted in a different color. To the right of the model in orange there is that gold-dominated structural block. The remaining blocks are silver-dominated at surface and where most of the historic drilling targeted and indicated there's silver. It was only later that we found out that orange horizon with the gold mineralization dips under the silver. So shown in the discs are bedding measurements. There were a ton, and we're just showing them in different colors to show the changes in the dips. So Warren made these, and we had no oriented core. And so we had to interpret the subsurface using surface bedding measurements. And this was important because we knew this is strata-bound deposit. So modeling bedding really was going to help us target untested silver with some sort of, we felt, knowledge of what grades we would be encountering. So lithologies were populated using downhole visual logging, surface mapping, and note the visual logging from RC drilling. And further, there was drilling from 8 diamond holes. And then some historic cross sections by Fletcher. So the purple, blue, pink, yellow horizons, like those are not individual stratigraphic horizons per se. They're just the control on the shape that we started with using the bedding. So chemistry is my favorite. So we improved what you just saw there using chemistry. We didn't have a lot of whole rock X-ray fluorescence analyses, which are really what is kind of best to start with to come up with your rock types. It's expensive and time consuming to complete, and we weren't in a position to go and do a bunch of reassaying of pulps for a whole rock, also because it uses quite a bit of material. We did have a wealth of historic ICP data, however. So we wanted to investigate other ways to assess rock geochemistry, rock types, alteration using ICP and also portable XRF. So to do this, we did submit some samples for whole rock from mineralized lower Barstow rocks using some historic diamond holes we had from Pan American's work, and 4 new 2022 RC holes when our program started in, I think it was April 2022. So Chris could say that the results from the different methods compared very well to each other. I feel like Chris is a little better talking about this stuff because like I don't get to do much geochemistry anymore. So bear with me if I say something wrong. But he was very happy with the results. I was happy with his confidence in the results of the different analytical methods and how they showed very good relationships to one another. So for example, the upper left, aluminum by ICP versus aluminum by whole rock XRF, very good match in the data. And so we could favorably use, we felt, 4-acid ICP data with PXRF results, and I'll get to details on that later on why. But basically, we could then use our ICP data to characterize rock lithologies, try to quantify hydrothermal alteration, and it also allowed for the assessment of association between indicator elements and metals. So like I said, I'm not going to go through like how to do these things exactly, but I'll just tell you, you know, what we did. So a first start really when looking at your multi-element data is to understand your data before you make any assumptions. So look at patterns, see if you can identify obvious error or bias, identify outliers or anomalies. Can you see relationships between elements? Essentially, you make lots of plots, univariate, multivariate. I'm shameless plug, IOGAS is your friend. It's my favorite program. It's incredible what you can do in it in far less time than in Excel. And really, it's easy to use. Any geologist can benefit and learn from it. So probability plots are excellent. Inflections in the calcium curve, for example, shown on the upper left, they can represent analytical bias. So these sort of plots you want to do just using one method, one analytical method, ideally using the same machine, etc. But the inflections can show changes in primary rock chemistry or hydrothermal alteration effects. So in order to determine if these patterns or breaks make geologic sense, they must make spatial sense. So you want to plot them in your model. So this is downhole data, and you can see some breaks. You can easily color code, you know, one quote unquote population different than another, put them in your 3D model and see if they make spatial sense or if they're mumbo jumbo. If they make spatial sense, you're on to something. So in our model, after defining, oh wait, did I miss a slide? No, I didn't. Okay, after defining the main bounded domains that I showed you, we wanted to model that Barstow pick handle contact. We did not have a lot of drilling of that historically. I think, yeah, it was only Pan American drilling. So ASARCO didn't do a lot of drilling that deep. That's right. So the reason why this contact's important, I mentioned, it's where the silver disappears and gold appears. So gold is hosted in both that lower pebbly conglomerate of the Barstow and the upper volcaniclastic pick handle. And those were hard to tell apart. So could we see, and not always, just sometimes. So could we see in chemistry the difference between the two? So if there were drill holes where the geologists would say, you know, they can't tell the difference, could we then use chemistry to confirm what rock type they were looking at, so we could just refine the model, you know, be confident in this is the contact despite inconsistencies or unsureness in visual logging. So turned out this was super easy chemically, as is a distinct change in the aluminum vanadium ratio across the contact. Why aluminum vanadium? Well, by examining, really you want to first look at your immobile elements, comparing these to each other. So elements that, quote, you know, you could say they don't move during alteration and weathering, but in sometimes, and I'll show you later in one of our things we've discovered, they give the appearance that they've been leached. But so examining immobile elements and comparing these to each other and to key mobile elements that are important for your mineralized system can add a lot of value here. So we identified that this ratio could help us fingerprint these two different rock types. So pick handle rocks have a much higher aluminum vanadium ratio than the barstow rocks, and the silicified barstow rocks also are slightly different. You can see they plot down more towards origin. So once these these values were plotted down hole in 3D, that contact just lit up. And so this in particular allowed us to have more confidence in defining gold mineralization later on. And really saying to the drillers, so the drillers, for example, I mentioned it was white friable rock. When they were starting to get towards the contact, they'd hit the white rock and they started calling it moon dust. But they didn't know when they didn't always know when they had crossed the contact, right? So we could use the PXRF at the rig in the moon dust and, quickly calculate a ratio and say where we were. Video. Working? Yes. Okay. So here's just a visual of that change. It's striking in the ratio. And we could put that in 3D and, like I said, just refine the model. Because, all of these holes have been logged. It really helped in some, maybe the historic logs. I think we relogged maybe half of the historic holes, so not all of them. So it really helped to just improve our confidence in the model. Here's another example of the value of immobile elements and plotting them down hole. So Chris noted a marked depletion of certain elements in certain sedimentary horizons as our new 4-acid data, ICP data was coming in for 2022. So these XY plots of some of these elements, such as titanium, aluminum, thorium, and scandium versus strontium, show a distinct negative correlation. And high strontium, which also equated to high barite values. So it's hard to analyze barium by this method because it doesn't digest well. So you can use strontium as a proxy for barium if that's important to you. Story for another day, literally a whole nother talk. But so elevated strontium, where we knew there was high barite, correlated with low immobile element values. Because we didn't have XRF data, we also didn't have silica, which of course highlights these silicified horizons. So we could use these element relationships to highlight what we interpret as exhalite horizons, which consisted mostly of silica and barite. So either the initial concentrations of these other elements, which are typically immobile, were either very low, or the influx of high concentrations of silica and barium gave them the appearance of being displaced or leached. The reason why this horizon is important is both at Langtree and Waterloo, the highest silver grades occur under this horizon. So we wanted to map these things out. And this, like I said, Chris is a wizard. This kind of stuff was a little over my head. He did a cluster analysis exercise using historic data, only because we wanted to, I think I mentioned, wanted to use our model as a tool, a dynamic tool during drilling. So what could we learn from what we had already, so that we weren't really starting from scratch with our own drilling. We went in there with all the knowledge we could to plan our program. So he used Gaussian mixture modeling. It's a statistical analytical tool that identifies distinct groupings of elements in your geochemical data. So it can be used to understand relationships between samples and interpret processes. So he used the 4-acid data from historic drilling and then an element suite appropriate for our deposit. So if we already had an idea of low temperature, hot spring, epithermal, he could pick an element suite that would provide the most value. So results showed 4 clusters that highlighted geochemical zonation in the deposit. So again, it spits out these clusters. You still have to plot it down hole, plot it in your model, see if it makes sense spatially. And it really did. Results showed upper volatile rich and lower volatile poor silver horizons. I can't tell you, I know the answers as to why they are like that. These are the kind of things where we try and have discussions with Warren, for example. He's UK based. So we'd have discussions at funny hours about, why we're seeing what we're seeing. I can't remember it all, I must say. But so beneath these were an oxide rich zone with more iron and manganese, zinc and lead oxides, and then gold mineralization just underneath that. And so you can see here in the red, the gold straddles the modeled Barstow pick handle contact, and Chris has his zones plotted in the holes here. So we could then take all this to define essentially a chemostratigraphy. So we didn't have, as I mentioned, oriented core. We didn't have core really much at all. We had 8 holes. So, defining the difference in the stratigraphy is hard with little chips. So chemistry really helped us out, supplemented the visual logging, and also helped us understand the metal distribution with more confidence. So interestingly enough, Chris likes to say this silver deposit is the best behaved deposit he's ever seen. We could, because we well understood the horizons where silver was hosted, we could literally almost predict the grade of silver we would get in a drill hole. Yes, like I said, the deposit's well behaved, but we did a lot of work to put in to understand the distribution in order to be able to achieve that. So it was really highly successful in that regard. I can't, of course, most deposits probably aren't quote unquote well behaved, but you can say maybe this is a method you could use for other strata bound disseminated deposits. Despite the folding in the rocks, that's where those bedding measurements came in. It's not well represented, say, on this particular section, but there's other sections where the beddings measured on surface indicate strong folding in the rocks, and of course dipping towards the Calico fault, and we see that in the distribution of the silver data. So this is just, I think, oh, let's do this again. Will it do it? Yeah, because I didn't even talk to this. So here's the stratigraphic model essentially. The purple there is this upper, we showed it as chert, but on the figure, but because Warren was calling it cherty, but it's not actual chert, it's silicified, kind of like a jasperoid. And there's 2 of those horizons, and then the highest grade silver occurs underneath that purple one. Again, the Barstow pick handle contact, the pick handle lights up in your aluminum vanadium ratio. And then in purple there is your thorium. And we could really see those silicified horizons lit up with just looking at thorium. So not even getting fancy with element associations. Finally, I'll finish up soon, the portable XRF. So initially during our program, our 3D model was updated iteratively, as lab assay results came in and multi-element data. But so we had a good understanding of the deposit before that, but as our knowledge of the deposit developed with our own new data, and of course, even just talking to the drillers and what they were seeing, we could begin using the PXRF while drilling, which literally allowed us to update our model in real time. So it allowed for rapid model evolution, but also allowed us to optimize the drilling. So for example, there's element relationships that I'll get to the next slide that indicated gold. If those vectors to gold weren't there, we could terminate drilling in one particular area and move on to another area. Risky, yes, but it worked out well for us because we felt we understood the stratigraphy well. So just, little disclaimers, PXRF is a valuable exploration tool because it gives you instant feedback on your chemistry, but there is a large amount of error on the values you get, specifically sample error. So you measure 1 point, it gives you a value, and an error range, you can measure that 0.5 times and get, of course, different measurements. So in order to use this tool effectively, you need to balance your understanding of the error, but with your data quality objectives. You cannot be using this tool to say, this value gives me, oh, there's 100 grams per ton silver. That's not how we used it. We didn't need an exact measurement or perfect data to achieve our goals. We just needed an indication. So we would calibrate our tool on historic pulps, compare the measured values to what the ICP showed us on those pulps. And so here's an example of lead, for example, on RC chips. We did RC chips, pulps, and then some surface rock samples. And so the key to success here was response ratio, which is basically what you saw in that aluminum vanadium ratio. So it's not necessarily that it's a particular value. It is, you know, if it's above background, if it relates to a certain metal you're looking for. So what we found in looking at our multi-element data was that lead and copper were very valuable for suggesting that we had gold mineralization that was high enough grade to drill, follow up on. And lead and copper are metals that are measured very well by the PXRF. Gold is not. You can't reliably measure gold with a PXRF. So what we used was lead and copper. You can see on the figure here, for example, most of the 1 gram per ton in gold, 1 gram per ton gold and greater really are associated with, you know, lead above 1,000, copper above 100. So we weren't going with those concrete values. It was just a guide. So lead and copper were vector elements to gold for us and helped us target this gold mineralized horizon beneath silver that we had an initial sense of from like 5 holes of Pan American drilling, but no one had ever followed up on. There's I believe, a lot more gold here. We've only scratched the surface in exploring what's exposed on surface, because it was kind of an aside. Our original goal was silver resource, so it was great. We got to add gold to it too, as well. And that was really because of the value of our chemistry and what we did with it. So I thought about showing this earlier, but here it is now. This is just our mineralization in that structural model. So we have this whole Barstow sedimentary package, like right down to this is the Barstow pick handle contact, is mineralized with silver. We, in our mineral resource estimate, used 50 grams per ton as our economic lower cutoff. So all you're seeing here is 50 grams per ton and up in terms of grade shells for silver, but the entire package holds silver. You know, this horizon underneath the 50 is about 25 grams per ton. And then here you can see the gold mineralization we've now modeled, and Chris has highlighted here our Gaussian mixture modeling horizons, our chemostratigraphy. So I just like this figure. It's we wrote a paper as part of that desert symposium. You know, it's just published in the volume for the event, but this was kind of our summary figure, showing the value we got out of looking at chemistry. And it wasn't that you know, there were old cross sections, for example, that mapped horizons, stratigraphic horizons, and the Barstow pick handle contact. All that old data was so valuable. What we did here was just give ourselves confidence in visual interpretations, give ourselves confidence in historic interpretations, and highlight things that well, we know, for example, really the gold just hadn't been highlighted before. So for us, in summary, you know, key rock forming and hydrothermal elements were really used to identify cryptic relationships between rocks, so differences that couldn't be identified visually. Highlighted higher grade silver zones, for example, underneath that silicious horizon, and allowed us to effectively target more or higher grade mineralization almost in real time using a PXRF and indicator elements. So next here, this project has a lot of silver in measured and indicated because of the challenges with the drilling in terms of core drilling and having to use RC. We really need to do a dedicated geotechnical program. So it wasn't ideal to try and do geotech work at the same time, have a core rig and an RC rig. It's just going to be technically easier to focus on that. So that would be the next step here. So basically, here's the people, some people, definitely not all. There's Chris there in the middle, Warren in the middle. Isabel is our resource geologist. She did a lot of our internal resource work, Stefan, project manager on the project with Alan O'Connor. I don't think Alan is in there, but then there's the team with the drillers. So yeah, I mean, teamwork makes the dream work. So that's what we did.